Okay, so this is lecture 21st. So let's go to the homework announcement first. In the last few lectures, we had no homework because I thought that actually Shaped-Goodman scheme is quite important and a little bit difficult to implement. So that's the reason why I gave you some time to catch up our lecture progress. We had sufficient time, so now it's time to announce our next homework number 17. I think that this homework is not that easy, so instead of 2 days term, I will allow 1 week for prepare your homework number 17. So please note that this is next Monday, and we have only one problem. Calculate the ID versus VD curve of double gate MOSFET shown below. So this is the exactly same as before as homework number 10. At the time you calculate it, but now you fully understand how to calculate the terminal current. So by using the Shaped-Goodman scheme, please calculate the ID versus VD curve. Of course, this device has gate contact and source contact and drain contact. Of course, source is grounded and you apply certain bias voltage to drain and also your gate. Of course, these two gates are tied together, so same bias voltage is applied to this device. So when you calculate ID versus VD curve of this device, please consider several gate voltages from 0 volt to 1.1 volt. So my suggestion is just to calculate. So Vz equal to 0 volt, 0.1 volt, 0.2 volt, blah blah blah, up to 1.1 volt. You may have many different cases, and for each of them just to change your drain bias voltage, then you will get the different ID value and just to plug it. So that is my suggestion for you. Okay, so do you have any question about this homework problem? So you know, this is quite closely related with our final presentation. So that will be the basis for our final presentation. So your final presentation. Let's go to our today's lecture. So today's lecture is now related with a very interesting and tricky implementational aspect of our lecture. So basic philosophy of this lecture, in the entire lecture, is to avoid many implementational issues as much as possible. So the basic philosophy is just to motivate you to have some interest on this numerical analysis. That's the reason why many times we just calculate one-dimensional structure and uniformly spaced grids. So that's the reason why we wanted to make it clear and as simple as possible. So I think that we have succeeded to that. So we have already spent September, October, and half of November. So 2.5 months is spent for that purpose. So I think that you are fully educated now. So we can just slightly go into the implementation. So that's the reason why I have prepared this today's lecture. Okay. So in this slide, we are now talking about box method. Fortunately, we have already covered this box method. So let's just review the box method. So box method is frequently called as finite volume method. This is two different names for the same method. So here we have certain equation written in the differential form. So you can easily understand this is quite a general form which is valid for Poisson equation and continuity equation. For example, if we consider Poisson equation, then it can be written as this form. And also, when we consider electron continuity equation without generation recombination term, then we will have this form. Of course, when we have this whole continuity equation, then we will have this form under the steady state condition. And think about this one, even when we have generation and recombination condition, still we have a certain modification in this and that position, but that is just a form of source term, just like right hand side. So this is quite generic for our purpose. Then this is the original differential form, and when we integrate it over certain small box, yes, small box written as omega, then of course the right hand side will give us just integrated as over a small box or small finite volume. Yes, that is quite easy. And left hand side, what happens if we integrate it over small volume? Then by divergence theorem, then now we can convert our volume integral into this surface integral. Here round omega just means that the surface of our finite volume or box, and here we have dA, and this is also infinitesimal area vector which is normal to the surface. So now you can understand this conversion because we have already covered it at least 2 times in our lecture course. The definition of a Born cell is identical to the definition of a Wigner-Zeit cell. We have a node in our device, so discretize with nodes and calculating the volume. Within that volume, every point has the closest node to the center node. You understand up to here? So how can we set this omega? So what will be the form of omega? That is my question. So natural answer will be the Bernoulli cell. So say that we have many points here and there. Then natural question is, now we understand if we integrate the equation over certain small box covering or surrounding the center node here, then in every form of omega we will have this equation. So say that we say this is our omega, or this is our omega, or this is our omega, or say this is our omega. Whatever form or whatever shape of omega is fixed, but anyhow this equation will hold because this is just the original equation integrated over arbitrary small volume omega. So therefore selection of omega is an important one. So now we understand actually the selection of omega itself is quite arbitrary. Any arbitrary shape is allowed. However, let's just think about this one. Here we have many points, and if we have a certain position, then this position is quite reasonable to be belonging in this point. If I say my omega is covering in this way, yes, still we will have a valid equation, but I think that that is not that reasonable. Oh, sorry about that. That will not be very reasonable. Why? Because there is no strong preference on this point. Why? This one should consume a lot of quite a large control area. Instead, this one has a very narrow and very narrow and very narrow control area. Is there any reason for us to love this position and this point? These points are not as important as this one. No. So I think that we have to treat all points as equal basis. So that's the reason why the concept of a Voronoi cell is preferred in this situation. So although selection of omega is quite arbitrary and up to you, however, instead of arbitrarily selecting the omega, so small volume, based upon the distance from certain position, we try to find out the volume. For example, this one should be clearly belonging to this node, and this one, of course, also this one. All points nearby this center node should be belonging to this center node. And how about this one? Yeah, sure. Then this one. How about this? How about this? So we can easily understand nearby certain point, then we should have certain volume. Yes, it is certain. It's certain. Also certain. Yes, all of these area is certain to belong in each position. Of course, we have a certain. Then what will happen inside it? Then if we expand it, and eventually two boundaries will meet, and when they meet together, then we have to anyhow decide what should be the boundary between them. If we are talking about the distance-based selection, then quite naturally, if we have distance and the equal distance point, so midpoint between them should be the point where we make the boundary. The relation also holds between different two nodes. For example, if we have two different nodes and connecting them, and just midpoint will be the starting point of taking the boundary. Here we have this one, and here we have also this one, and here we have this one. Yeah. In many cases, so in many edges connecting two different nodes, we can think about these boundaries. Yes. Then, of course, by doing this action, for example, let's say that we will have a certain polygon by action of this operation. Then we can say that within this new volume or new polygon, it is certain that the closest blue point is the center one. All of these black points are belonging to center blue point, blue node. So you can easily understand this procedure. So if you wanted to find out the Voronoi cell where all points inside our space whose closest node is the center node is given by in this way. So just to calculate the normal line with respect to the edge, then collecting them all, then you will get a polygon. Then the interior of that polygon will give you the Voronoi cell for this center node. Although my explanation is not very clear, but I hope that this concept is quite appealing. So anyhow, we have to divide our real space, and based upon the distance from each node here, blue dots here in this example, based upon the distance from all of these blue nodes, a point is just to count belong to one of them. For example, if we set arbitrarily a certain position, then we just calculate the distance, and distance. Yes, distance to all nodes can be calculated, and try to find out the shortest one. So which one is the shortest? Okay, for example, let's say that this is the closest one, and this point is now belonging to this node. Then collecting all the positions which is belonging to this node, then it will build up the Voronoi cell for this node. Now let's go to the next slide. So I'm just talking about how can you calculate the Voronoi volume. This is actually related to the definition. So within a Voronoi volume over a certain center node, the closest node is always the center node. So let me just repeat again. Here we have many nodes. However, within the Voronoi volume of this center node, then let's say that this one, then when we evaluate the distance to every node, then the shortest one will be always this center node. That's the reason why this point is belonging to this node, this position is belonging to the Voronoi volume of this center node. So if we have a position which is close to another node, then obviously when we calculate the distance, then it will be revealed that the shortest node or shortest distance is made from this node. So then this point is belonging to that node point. So that is quite easy. However, we cannot make this kind of evaluation for every point. So say this point, that point, another point, another point. That is not possible. So, it's not possible. So instead of that, just to calculate, first of all, think about edge and find the midpoint. So calculating the midpoint is quite easy, just taking the half position and try to draw a line which is normal to edge. So here we have an edge point. This is perpendicular. Then it is certain, neglect all of these surrounding points. Just to concentrate on these 2 points. Then in the left of this line, yes, every point is belonging to this one. And right side, then every point is belonging to this one. So our calculation of Voronoi volume is quite simplified by just calculating the interior of this polygon. So between this and that will be the line. And how about this one? Between this and that, we will find out the midpoint and find out the perpendicular line. Then here now, these points have 2 properties. Between this and that, the center point is more close point, and between this and that also lead center point is closer point. And how about this? Of course, we can also draw in this way. However, this is already covered by this intersection of these 2 lines, so that doesn't contribute. So for every pair or for every edge, we can try to draw edge and take a midpoint and draw perpendicular line. When we collect all of these lines and try to find out the polygon generated by these lines, then it will give us eventually a volume here in this 2-dimensional case area, which is corresponding to the Voronoi cell. Now you understand, in order to calculate the Voronoi volume, so Voronoi volume here omega for our purpose, then we have to calculate in this way. Then calculating every time the perpendicular line and try to find out the polygon. Yes, that will be the method of our interest. Then why don't you just consider a practical example. Here we have a pentagon. Here pentagon means that yes, this is a pentagon. Also, okay, although that is not convex, but anyhow, this is a pentagon. Yes, we have 2 pentagons, and these pentagons are discretized with 6 points. So here we have 5 corner points. Yes. Also we have 5 points and 1 inner point here. Yes. Can you clearly see it? So here we have one inner point. So let me just calculate the Voronoi cell from these two cases. Then what should we do is just to think about the center node and all surrounding points. Here we have 5 surrounding nodes, so we have to care about first edge, second edge, third, fourth, and fifth. After that, so calculate the midpoint, and midpoint, and midpoint, and midpoint, midpoint, and draw the line perpendicular to midpoint. So yes, we will have a certain line, and we will have a certain line, a certain line, certain line, and yes. Then try to build a polygon. Yes. Then you will have a polygon like this. So you can easily understand the red box I have drawn already in this slide just to represent the Voronoi cell omega corresponding to this center line. Of course, Voronoi volume can be defined not only for this center node. Of course, we can think about the Voronoi volume for other nodes. For example, why don't you just consider the Voronoi volume for this node? Then what will happen? Exactly same as before. Think about the connecting edges like this and like this and like this, and try to draw one line. Of course, here we have one line here, but this is just to meet with our another line on the edge, so nothing. And think about this one. Then how about this? In this case, we have midpoint around here. I'm not quite sure. Yes. So yeah, my eye estimation is given here, and let's say this will be the normal line. So in this case, the Voronoi cell for our this black points is simply given by this black shaded area. Okay. Of course, we can also try to find different nodes. For example, yes, for this node, now it is clear that that will be the Voronoi cell. And how about the other one, like this one? So here we have also three surrounding nodes, and here we have one, and another one is corresponding to this way, and third one, of course, here we have this line, but that is meaningless. So we will have this one. Yes. So everybody is now understanding that this is the situation for calculating the Voronoi cell. Let me just finish our discussion here and here, and also somewhere between here. Yeah, that will be also the Voronoi volume for this red colored one. Oh, okay. Then now we can decompose all of course here I have to be a little bit careful about this point. So that will be the point. Yes, that will be the Voronoi cell. Now you understand, by this way we can decompose our entire area, two-dimensional plane, into many Voronoi cells, and each of them is belonging to each node. So now we can calculate the equation shown in this form without any ambiguity. Now, just following the Voronoi cell, then we can every time calculate this integrated form quite clearly. That is good news, but think about this one. So that is really good news for our calculation. But one thing we have to keep in mind is, now we have the center point, and we have surrounding edges. So this edge has the length of a perpendicular line, this one, and also for this line, yes, we have the length of a perpendicular line like this. And even for this line, our length is, although that is not that long, but here we have it. And for other edges, for example this one and that one, we have still yes and yes. I mean that in this left example, every edge connecting our center node and 5 surrounding nodes have non-zero lengths. That sounds quite obvious up to now, but let's have a look at a counterexample I have prepared here. Here we have center node and we have 5 surrounding nodes, and this is the red box is Voronoi cell. How does it look like? It just looks like a it's not pentagon. For example, for an edge here, of course we have non-zero length. And how about this one? Here we have non-zero length for this edge. And how about this edge? Can you find any length corresponding to this edge? My question is, there is no length corresponding to this edge. Previously, we had, although small, we had certain length assigned to this edge, but we have no length now. And how about this? If we consider this short edge, then we have here, this is the length, perpendicular line. And finally, if we consider this edge, then this is the length. The point is, okay, evaluation of Voronoi diagram, Voronoi cell, that is obvious, and every time when you have a set of node points, then you can calculate it. There is no ambiguity. So every time the volume or area can be divided by following a simple rule. Just to draw a plane over line perpendicular to an edge. Yes, then you will get certain polygon or polyhedron. Then you will get the Voronoi volume or Voronoi area, Voronoi cell. Here, in this right figure or right example, is this correct Voronoi volume? Yes, it is a Voronoi volume calculated in a correct way. But here, it has no connection between this and that. This edge is actually meaningless. Then what does it mean? Actually, in this case, although we have discretized in this way, here we can find one triangle, two triangles, three triangles, four, five triangles. Actually, the edge connecting this and that is meaningless. So better way to do this or better way to divide our space with these triangles is just to suggest that then in this case we can think about 1, 2, 3, 4 surrounding nodes only. Okay, if we consider this way, then it will be quite obvious to have 4 surrounding nodes. Then we will get the position like this. So I mean that sometimes the concept of Delaunay mesh and non-Delaunay mesh sounds quite complicated, but point is here Delaunay mesh is, simply speaking, if you have non-Delaunay mesh like in the right example, then your Voronoi volume and your division of your space into triangles does not correspond perfectly. So there is some difficulties in this non-Delaunay mesh. So that's the reason why people try to make a mesh to satisfy Delaunay discretization. So maybe you are curious about what is then the Delaunay condition. So here you can find this one. When you have a look at this triangle, then its circumcenter can be calculated. The circumcenter is here written as a square. Yes, this is the circumcenter of this triangle. It means that the distance between this circumcenter and corner point here, another point, and another point, this is all of these distances are identical. So now we can build a circle which is connecting this node and that node and another node, and you will find a certain circle. This circle is called as a circumcircle. Yes, and the Delaunay condition means that here we have another node, and this node is not inside the circumcircle. Simply speaking, the Delaunay condition means that when we draw the circumcircle of each triangle, then there will be no node point inside this circumcircle. This right example just shows the counter example. Here we have the same circumcenter, and this black circle is corresponding to circumcircle. However, you can easily find that this one is inside the circumcircle. So, in this case, when you evaluate your Voronoi volume, and the Voronoi volume has many sides, and the triangle side and Voronoi volume sides are not corresponding to each other. So that is the problem. I think that in this part, actually, when I started to talk about Delaunay condition, maybe some of you are a little confused. So if you are not fully convinced with this Delaunay condition, then I think that it's okay. Point is, we have to find out the Voronoi volume based on the distances. Yes. So when you calculate the Voronoi volume, then you can find the side of Voronoi volumes corresponding to each node, and that will be used for evaluating your equation. I see that this is too ambiguous, so I have prepared a concrete example. So think about Poisson equation. So Poisson equation, here we have left-hand side term. So surface integration of vector field, in this case D field, over surface area of our Voronoi volume. And let's say that this is the volume, and here we have a center node called 0 node, and surrounding nodes starting from 1, 2, 3, 4, 5. Of course, this Voronoi volume is now denoted as this red polygon. This red polygon just shows the omega, and what is the round omega? If we are talking about round omega, then it will be actually the lines like this. That will be the round omega. So explicitly, it can be written as this form. This integration can be now decomposed into 5 sides of our Voronoi cell. The first side, second, third, fourth, and fifth. In this case, we can divide it into 5 pieces, and we can define the vector along this direction, and that direction, and that direction, that direction, and another direction. And this component along this direction is written here as F connecting 0 and 1. This component is written as F connecting 0 and 2. This one will be F connecting 0 and 5. So this is the field connecting 0 and ice node, surrounding nodes. And of course, we have to think about this infinitesimal area component, and now it is quite clear. If we say F01, then we have to also consider the area perpendicular to this edge, and this is here written as normal area A sub A, which is corresponding to, or which is normal to edge connecting 0 and 1. So that will be also edge connecting 0 and 2. This one will be area perpendicular to an edge connecting 0 and 3, blah blah blah. So you will have this notation. So I think that we have not covered the remaining lecture contents, or a short remaining lecture contents, but I think that we have plenty of time to cover the remaining thing. So on Wednesday, quickly covering the remaining some materials, then we will move to different topics. But please understand, in practice, this meshy or constellation of unstructured meshy is quite important and quite critical for building a practical simulator. Okay, thank you for your attention up to now. So maybe you feel that the thing is completely changed from some certain physics or discretization, but now we are now talking about some computational geometry a little. But you know, the building of device simulator is based on many different aspects of different fields. So please understand this situation. Okay, now time is up. So let me just wrap up today's lecture. Thank you. Bye.